Evaluating logarithms, 8.3. So remember the thing I told you to remember and you're going to forget, and I told you to remember like 7 times and you're still going to forget? You need to know this property for logarithms, how to go from an exponent to a logarithm and back. So we're going to use this property to evaluate these logs. Probably don't need a calculator. This is the whole point of certain questions. And then eventually we're going to see how we can use a calculator or just approximate the value of the logarithms. So first we want to rewrite this as an exponential, then evaluate. Now remember, this is the base. It's a to the y equals x. So 4 to the what equals 64. And that's what I write down. 4 to the what equals 64. Now, you chemistry guys, you probably want to find the log of both sides to find that unknown exponent. But if you can break down a power or a number into a power with the same base, then you don't need a calculator. You can just get there using your knowledge of exponents. So this is 4 to the y, and I know 64 is 4 to the 3. And as soon as I set them up with the same base, I could just equate the exponents. Y equals 3. Done. Okay, you probably should have learned how to solve exponentials like this even in grade 11, but maybe some haven't because of your calculator woes. Here we have a log. Again, 3 to the what is 1 over 27. Let's write it down. 3 to the y is 1 over 27. I know 27 is 3 to the 3, but it's 1 over 27. So this is 3 to the y equals 3 to the negative 3. You can show an extra step there, 1 over 3 to the 3, and then turn it to the negative exponent. But not necessary, it's pretty easy, it's 1 over. So I can equate my exponent now, y equals negative 3. Next one, 2 to the something equals negative 4. When this value is negative, you can't solve this. There's nothing I can raise 2 to the power of to get a negative number. Every power is positive, unless there was a negative in front of there. That base would have to be negative, but we don't do that. So this is actually not possible. Okay, there's nothing I can do to get 2 to the y equal to a negative 2 to the 2. Like y would equal 2 if this was negative, but there's nothing I can do there. Let's bring back our knowledge of radicals. Okay, so I'm going to say 5 to the y equals the third root of 25. And then I'm going to remember how to change this third root of 25 into a power. This is 5 squared. And the index of the radical is the denominator of my exponent. So this is 5 to the 2 over 3. So remember how to change those radicals. Okay, we'll give you a little reminder over here. A root b to the x, we'll say. Actually, go the other way around. X to the b is x to the b over a. Okay, we divide by that little index in there. Usually it's a 2, unless it's written otherwise, like a 3. Okay, so now we know y equals 2 over 3. Done. Now, these are easy because they're nice numbers. I can do them without a calculator. Eventually, you're going to have numbers that you have to approximate, and eventually we're going to get better at approximating, even getting pretty exact as we use logs to solve equations. So, notice how there's no base in some of these. Okay, the ones without a base, these are called common logarithms. It just means the base is 10. Okay, so sometimes, because the base is not written, this doesn't pop into your head. But you have to know that a common logarithm is written without that base. This is just 10. So I'm rewriting this like 10 to the something is 10. 10 to the what equals 10. Well, I know y equals 1 here. That's an easy one. Same thing. 10 to the what equals 100. Now, I know this is going to be easy, but I'm still breaking this down into an exponent. So I can equate the exponents, y equals 2. Next, we have 10 to the something equals 500. Okay, nothing I can really do here. I could play around with it and say this is 5 times 100. 10 to the y is 5 times 10 to the not really. Not really. Not even worth it. Okay, so what I can do here is I actually have to do some trial and error with my calculator. So I'm going to say 10 to the exponent of 2.5 is 316. I'm going to go back, I'm going to change that 0.5 to a 0.7. 501, that's definitely good enough for an approximation. So 10 to the 2.7 is 501. 10 to the 2.7 is 501. Therefore, y is approximately equal to 2.7. Notice the question says approximate. Can you find the exact value? Of course, but not today. Okay, I chose 2.5 first because I know 10 to the 2 is 100 and 10 to the 3 is 1,000. So 2.5 maybe is 500. I know it's exponential, so it's going to be a little higher. And then I just honed my approximation from there. Here we have another one. 5 to the something equals 47. So I got to do some trial and error. I know 5 squared is 25 and 5 to the 3 is 125. So I don't know, 2.5, 2.4. 5 to the 2.4 is 47. Totally just guessed, I swear. 47.6, therefore y is approximately equal to 2.4. Okay, pretty straightforward. Might take you 1, 2, 3 tries depending how good your estimation is. I know a lot of people don't like estimation, but look how quickly I estimated those because my estimation skills are good, right? So it's not useless. You know, kids ask, oh sir, can we just like use our calculator and find the answer instead of estimate? No, estimate and then find the answer. Almost always when you do math, you should kind of stamp yourself with an idea of what the answer is and then verify the idea with the calculator. If you do this all the time, your estimation skills get really good. Okay, and there's a lot of estimation that's very useful in math, more so than calculating. Okay, last part. Now these are just general properties, nothing new, but they look different and you're going to encounter them and you might make a mistake because of just how they look. They're confusing. So same thing here, 6 to the something equals 1. And just a reminder that anything to the power of 0 is 1. So here we have y is equal to 0. Okay, I know it's nothing new, but okay, so the next one, same idea. 5 to the something, so 5 to the y equals 5 to the x. So y just equals x. It doesn't matter what that value is up there. It could be a number, it could be an equation. Okay, just going to be y is going to be equal to that something up there. The number, the x, the equation, who cares? This one, in my opinion, is the hardest. Probably not, but just my brain loves to go from log to exponent. I'm not too fond about going from exponent to a log, especially when there's a log in the exponent. But if you look at the definition of an exponent, it's a to the y. So this is the y value. Log 6 to the x is the y value. A to the y. The base is the base of the log. And x goes next to log. Sorry, that's supposed to be a y. Okay, and just like this one, this is just the inverse of it. Y is also equal to x over here. Okay, just, you know, it says general properties. I like to consider these like special cases just because they look different and they're kind of, should be solved quickly because it's just a property that you should know. Okay, and that's pretty much it for 8.3. Bring back your exponential skills and breaking down things into a base, very useful skill. Sometimes you have to use your calculator, but estimation is a good idea. And then there's 3 special cases, general properties.